So welcome to the second class of the second week. The purpose of today is correspondence analysis. I think most of you have never seen it, so I have to start from scratch, isn't it? Am I right? Okay. So, yesterday's class has been put on YouTube, and an additional file about acceptance of pull request. So have a look at the files. From next week, there will be my colleague, Professor Asadullah Khan, and tomorrow we both will be for the lab section and the competition as usual. So there will be something that you are required to solve tomorrow or during the weekend, right? Tomorrow? Tomorrow, no video. Tomorrow is just next week. Right. I will talk to my colleague because what is your opinion? You strongly want to have the videos? Because now you are used too well with me. That's the point. You know, if you have something, then you don't want now to lose it anymore. So the more pressing, so I have this blackboard, I have the screen, and so on and so forth. Next time we will start jumping on the table to entertain you as much as possible. No, yeah, okay. So I will do my best to convince him to put the lessons on YouTube. Correspondence analysis. Correspondence analysis will be the first chapter of book 2. Is again a dimensionality reduction problem. PCA deals with quantitative data. Correspondence analysis does the same for a contingency table. Right? So you want to reduce the dimension in a contingency table. But the framework is the same and the purpose is the same. Instead of quantitative data, now you have categorical data, both in the rows and both in the columns. So you have a pivot table, what we call the pivot table, a contingency table, where the entries are the frequencies. Oh, in PCA, you want to start from P and to have K, where K is much smaller than P. And then here you have the total variance, which is explained. Now, what is the total variance for categorical data? Because you have to explain the variability in the contingency table. Of course, the model is valid if a proportion of variability has been explained during this reduction dimension process. Also in the PCA, we have seen the B-plot, and the B-plot you show the P-vector, the arrows, and then the endpoints corresponding to the scores. Well, in here, you will see that you will do something very similar. So you project row points and column points. We are going to define what these row points and column points are. As in PCA, the required condition to properly apply PCA was that the variables were correlated. There was a correlation of the variables. You remember the example of the ball. If the data are on a ball, then there is no dimension reduction. On the other hand, if the data are on a needle, then there is a dimension reduction. There is here, same thing here. This makes sense just if there is a significant association between rows and columns, right? Okay, so you need to have this correlation. So, let us say the null hypothesis of independence must be rejected. You remember what we have done in the first course, Introduction to Data Science, where we have introduced the chi-square test. The chi-square test was a function of the differences between real frequencies, Nij, and expected frequencies. Okay, correspondence analysis does no distributional assumption, and then is a simple and powerful visualization method used everywhere and really everywhere. But okay, there are millions of people who use this method. The algebra inside is quite intricate. The algebra underline is a bit heavy, so I hope you'll be among the 0.01% who also know the algebra. So suppose now we start with the problem. This is a contingency table, and here you want to understand who are those most in favor of science, and what is the relationship with schooling level. Schooling level goes from 1 to 6. So 1 is primary school certificate and 6 is the PhD at the top. Then there is this from 1 to 6. As the years of education increase, how does the attitude towards science change? That's the problem. Okay, what are the rows which are mainly associated with which column? What are the combination of rows and columns that are mainly deviant, that deviate most from the hypothesis of independence? Right. So you can imagine, as in principal components, there is an underlying dimension that is pro-poverty or richness. Here there is an underlying dimension which is, I don't know, schooling level, something you cannot or not observe directly, or attitude towards scientific aspects, or, for example, there is intelligence or whatever. Okay, here it is another example. And occupation and schooling level. Which occupations are typical for given educational qualification? Which row is mainly connected with which column? Okay, so if you have a certain degree, you expect to do what? If you have just a primary school degree, you expect to do what? And then opinion on death penalty and political party in USA. These are real data. If you are Democratic or Republican, and then to each person has been asked, are you in favor, are you against, or you don't know? Right. So how the political belonging matters in the political opinion about the death penalty. Who does what in the family? You see, there are who does what, I mean inside the couple, who does what, and then there are a series of tasks. So you can see that correspondence analysis can be used for any contingency table, of a certain dimension. Because if it is 2 times 2, well, there is very little to do. Okay, soft drink and word. How is the image of your firm perceived? What is the word which characterizes your brand. Okay, this is also another very interesting problem because it says that your product is mainly consumed by young or by old. What is your target? Right. Notation in symbols. This is the contingency table. Therefore, capital I categories for the rows, capital J categories for the columns. Total sample size, small n. Capital N, the overall matrix of size I times capital J. Okay, the notation? Right. And then, okay, in the marginals, you have the margin, the total of first row, the total of the ith row, the total of the first column, the total of the jth column. Sorry, this is very trivial, but let me, okay, then, so this is matrix N. Then, contingency matrix, same thing, but you divide each entry by N, sample size, lowercase n, okay? So the sum of all the elements of matrix capital N is small n. The sum of all the entries of matrix P is 1, because you divide each entry by the overall total. Right. Okay, and then we work in matrix term, and in matrix term, these are the things. So the sum of all the elements is n, the sum of all the elements of P is 1. So this is in matrix terms. Okay, then an initial example that we have already seen in the first book about toothpaste dataset. So there are 4 regions of Italy and there are 3 different brands. Commercial brand, industrial or indifferent. Industrial brand is the one which is most expensive. Commercial is the one which is the cheapest. So, you have a new supermarket in a particular region. What do you expect that your customers buy? The cheapest or the most expensive? Well, no, it doesn't. You don't know. You don't know. For you, maybe it's the most expensive, but for a poor person, then it is the cheapest. Or if you are stingy, you always buy the cheapest. And so it depends quite a lot. And then Italy has been just a united country for 200 years, but in the past, people from Liguria were very different from people of Lombardy or from Piemonte, because we were divided into small villages. So there was really a big difference in the different parts of Italy. Okay, now let me introduce the masses. The masses are how important is a particular row with respect to the total, how important is a particular column with respect to the total. Therefore, these are the masses. The marginal relative frequencies. The total of row I divided by the overall, or column masses, the total of the jth column divided by the overall. Okay, you understand the rotation, eh? So n dot j, for example, n dot 2 is this number here. So the sum of this number. n1 dot is this number, so the sum of the row. Okay, and I dot, the sum of the row. And dot j, the sum of column j. Right. So this is the notation. Vectors R and C. The vector which contains the row masses, how important is each row with respect to the total, and then vector which contains the column masses. So you see, C prime, because it is, in this case, it is put as a row, because the vector is a column. If you write it in a row, C prime. Okay? Therefore, here you have this matrix P, so the sum of all the entries is 1, together with the column, with the vector, here there are the row masses, the importance of each row. The sum of these elements is 1, of course, and here there are the column masses. The sum of this row is 1. So this is vector R, this is vector C prime, the transpose of the column masses. Okay, matrices, capital DR and capital DC. Same thing, but put as diagonal matrices. Okay, so the elements of R form the main diagonal of matrix DR. And this diagonal matrix, that is all the entries which are not on the main diagonal are 0. Same thing for DC. So DR has dimension I times I, DC has dimension capital J times capital J, number of columns. Right. Now another concept, row profiles. You have seen it a bit in chapter 1 of the first book. In the matrix of row profiles, you divide the value Fij, you divide it by the total of the row. In the matrix of row profiles, you divide by each row by the total. In the matrix of column profiles, you divide each entry by the total of the columns. So you have the matrix of row profiles and the matrix of column profiles. Okay, so this is in symbol. Either this or this is exactly the same thing. And this is the matrix of row profiles. That if you want, you using matrix multiplication, this is the formula. Right. So P is the denominator as N. The R in the denominator, same thing, and so there is a cancellation when you take the inverse. This is obvious. Therefore, let me show the original matrix here, the vector of row masses, the matrix of row profiles. You see this 0.5 is 111 divided by 222, 0.5, the matrix of row profile. So you divide each entry by the total of the row. Therefore, 0.221 is 49 divided by this. Okay, 358 divided by this number here, and is 0.664. This is the matrix of row profiles. This is the matrix of row profiles. Row masses and column masses. Note that vector R and vector C prime, the transpose. Okay? So, therefore, this is like a matrix R, as we have seen. There is matrix X, a matrix of numbers, not of categories. And now you can do the same. This is for row profiles, but you can do the same with column profiles. So you divide by the total of the column, you divide by the total of the column, and this is the transposed matrix of column profiles. Right, because the column profiles C is 4 times 3. This is 3 times 4. Therefore, it is the transpose. Right. But is the same thing. Here you divided, instead of dividing 49 by this number, you divide 49 by 99. Divide by the total of each column in the matrix of column profiles. But the analysis is symmetric. You can understand, you can start on the rows or you can start with the columns. The analysis is symmetric. Therefore, okay, row and column profiles. For example, this is the matrix of row profiles, but the sum of these four elements is what? The number of these four elements. You have divided by the total of the corresponding row, so the sum of these four elements is 1. Goes without saying. Therefore, the matrix of row profiles is a matrix of capital I points in the space of dimension, which is dimension of the row points, is dimension capital J? No, because the final one is automatically obtained, because the sum is 1. Therefore, the analysis of the points, of the capital I points, of the row profiles, is an analysis of capital I points in the capital J minus 1 dimensional space. Because there are not J dimensions, capital J dimensions. The dimensions significant are J minus 1. The other one is linear combination of the other, because the sum is 1. Right. Same thing for the column profiles. Okay. Now, another concept. When I realized it, when I saw it during the PhD 30 years ago, I was very happy, because when I saw this concept, you know, sometimes you are happy about small things in life. Yes, this is how it is. And so, if you take the averages of the row profiles, you see these are row profiles, so you divide it by the column, the row total, and then you take the average, a weighted average. Well, you obtain nothing but the column mass of column J. Therefore, well, you can do it with the matrix multiplication if you want. Therefore, the column masses can be interpreted as the weighted averages of row profiles. Incredible, eh? Same thing if you do a weighted averages of the column profiles, that you obtain the row masses. Let us see. Okay. Now, all these concepts now are implemented in file which is correspondence. Where do you find the file? If you go to the repo, then you do the pull, then you have all the files for book 2, which is coming out. And so here you have to book 2, chapter 1, correspondence. These are all the files. So you'll find file correspondence inside book 2, chapter 1, correspondence, okay? Therefore, this book 2 correspondence, these are the files, and this is the file. This is the file, so our N, P, and then the profile rows, the profile columns, computes vector R and C, build the matrices DR and DC, Okay, let me run maybe this part here. So there are the vector R of row masses, column masses, then matrix DR, which contains the elements on the main diagonal, and then DC, same thing, then alternative matrix computation for C and R. When I put CHH, means another alternative computation. Okay. Therefore, let us see it. Now, if you, therefore, you do, this is the matrix of row profiles. If you do this number times this number, plus this number times this number, plus this number times this number, what do you get? If you do this multiplication, you multiply here the elements of the first column by this, and you take the sum. You obtain what? You obtain this number here. Similarly, if you multiply these numbers by these numbers, you obtain this number here. Right, and this is exactly what we say. If you multiply the row profiles times the total and you take the sum, you end up with f dot j, the masses, the masses of element j of vector C. Therefore, the last row contains the column masses, but the column masses are the centroid of the weighted centroid of the row profiles. Very nice interpretation. And now you want to see the distance. Clearly, in statistics, you want to see how a province is distant from another province. And here you want to see A is more distant to B or A is more distant to C. What is the distance between two generic rows? Two generic rows. Can you do something like this? Can you do something like 0.221 minus 0.02 squared, and then you take the difference squared and here the difference squared? Well, you have to take into account that the columns have a different size, have a different importance. So it is as if you work with variables that have different importance. Therefore, this formula is not correct, and in fact, because it assigns equal weight to all columns. Therefore, what you do is called the chi-square metric. Is a distance between two generic row profiles, but weighted with the inverse of the frequency of the jet column. Because here, what you want to do, here, you want to emphasize the distance between row points when it is large, even if the column total is small. As if you standardize the data in some way. Therefore, these column masses can be considered as the variances of the variables. So in the Mahalanobis distance, you divide by the square root, the inverse of the square root of the variance. Therefore, this is the generic formula for computing the distance between two generic rows. But as you have seen, there is the distance between two generic rows and the distance of each row with respect to the centroid. Okay, there is this one. But what is the centroid of the row profiles? Vector C, the vector of column masses. Okay? Therefore, here you take the distance of each row point with respect to the centroid. So you have three distances. The distances of A with respect to the centroid, of B with respect to the centroid, and C with respect to the centroid. Okay. But this distance is therefore can be interpreted as a square deviation from the mean, this distance. Right. So if you, and then, for example, these are the distances. These are the distances for each row and for each row profile with respect to the centroid. You see D1, 2, 3, the distance of each row with respect to C, the centroid of row profiles, the vector of column masses. And so you can see that row 1 is the one which has the largest distance. Similarly, the same thing for the columns. So most distant row profile is brand A, and most distant column profile is Liguria. Now, let us go back to this interpretation. So the distance is the square deviation from the mean. So if you weight this square deviation and then you take the sum, this is a weighted variance. Well, this is the total variance of the contingency table. The sum of the square distances weighted by the importance of each row. And this is called in the language of contingency table, the total variability of the contingency table, the total variance. Isn't it incredible that here there is a total variance? And this total variance is the distance of each row profile from the average, weighted, and as we will see, the sum of these distances, which is called inertia or inertia, call it as you like, is nothing but our index chi-square that we had seen in book 1 divided by n. Incredible. So this is the interpretation of the index chi-square divided by n. Therefore, can be interpreted as the total variance of the contingency table. Okay, you can do the same thing for then for the columns, and the implementation is here. So, square distance from the average profile, and then this dist I, the distance of each row from the average. Or this is the manual computation. This is the manual computation. Then the sum of the distances multiplied by the weight, the importance. This is the total inertia. The total inertia of the rows. But you can do the same with the column. And this number is exactly equal to this number. If you start with the row with the columns, it's exactly the same thing. And this number Ni is nothing but the chi-square divided by n. Incredible. Incredible. This is the theory underlying this contingency table. So therefore, the total variability is the sum of the variances in quantitative data. Here the total variability is this inertia. This chi-square divided by n. Now, as in multivariate analysis, so we start from matrix R, from matrix X, and then you want to obtain X tilde, the matrix of deviation from the means. X tilde, X minus once X bar. This is n times 1, and this is 1 times p. Right? This is in matrix notation, so you remove the averages. And here you do the same from R, and then you want to obtain R tilde. R minus 1 prime is what? The centroid is what in this case? The centroid of the row profiles. Here is C prime, the vector of column masses, which is the centroid of row profiles. But it is exactly here the same thing. That's the reason why here you have this formula here. So 1 is a vector of ones, okay? Then this is a weighted space where each row has its importance. And the weight is what? The weight is the importance of each row with respect to the total. And not only, you have a different variability of each column, and each column, this different variability, this DC, can be interpreted as the vector of the variances. And so this is the analogs of our matrix Z in a space which is weighted both for the rows and for the columns. Okay, and this is how you write. So what is now here? What is the sum of squares of the elements of Z? So in multivariate analysis, if you take the sum of squares of the elements of Z, well, divided by n minus 1 if you want, this is the total variance. Here, if you try to do the sum, here I also put divided by the sum of Fi, but this is 1. Because the sum of this thing is 1, the sum of the relative frequency. So the trace of this or the trace of this. So the sum of the squares of the elements of Z is again the total inertia. Incredible, eh? So you pass from the original matrix to a matrix Z, and then you take the sum of the squares of the elements, of all the elements of Z, and this is the total inertia, the total variability of the contingency table. Isn't it incredible? This is exactly our matrix Z for the multivariate analysis case. So, this matrix Z, if you want to project point in a lower dimensional subspace, and then you want to lose as little information as possible, what do? When you have a central matrix, well, you do the SVD, the singular value, the composition of Z. And then you see, this is our Z. So you want to have that the sum of squares of the difference between this matrix and Z hat is as small as possible. And this is minimized when you take the largest squared singular values, which are the largest squared singular values. And then once again you do this, the SVD, the SVD or matrix Z. This word SVD or matrix Z, therefore R, in this case dr to the 1/2, this becomes, if you multiply by dr to the minus 1, if you multiplied both sides by dr to the minus 0.5, this is what you obtained, that this matrix here, multiplied becomes the identity, therefore on the other side you have dr to the minus 1 divided by 2. Okay, 1/2. Therefore, the theory is exactly the same as a principal component analysis. So you have a set of coordinates projected into a new system of Cartesian axes. And these are the new coordinates of the points. Now, the output is very similar to the output of principal component analysis. Okay, you have the eigenvalues, which are the squares of the singular values. You have the percentage of explained variance. You have the loadings. You remember the loadings were the correlations between the original variables and the underlying components. Same thing here. Same thing here with the vector. So you see the vector, the points which are close to the axis that have a largest correlation with a particular axis. Then you have the score of row and column profiles. And then you have the communality. Remember that the communality was the percentage of variance of a particular variable which was explained by the first two latent dimension. Here is the same thing. Right. What is the variance of the particular point? The inertia of a point is its distance from the respective centroid. Right. So the inertia of the point that has to be decomposed into the contribution that the underlying dimension give to the inertia of the point, to the distance of the point to the centroid. So different ways of writing Z. You can have a look at the algebra, and then this is the last formulation here, says shows that the analysis really is symmetric. So you start with the wrong column points. Can you see the algebra? R, then you multiply the here by dr to the minus 1. You see, you understand this, eh? So therefore, dr times 1 is r. So the analysis is really symmetric. Therefore, the sum of the squares of the elements of Z is chi² divided by n, is the total inertia, the total variance of the contingency table. Sum of the weighted distances of each row profile with respect to the centroid weighted, or the column profiles to the centroid square distances weighted. So the analysis is symmetric. This you can write it this way, and then all this is implemented here. Construction of Z. CHK, you can see that what I've shown in the formula and what is implemented in MATLAB is exactly the same thing. You see all the matrices. And then sum, you see, sum of Z square all, the sum of all the elements, square elements, is again the total inertia. Let me run it up to here. So this sum here, the sum of all the elements of Z is the total inertia. The total inertia that had been obtained as sum of square distances of row profiles, or sum of the square distances of column profiles with, weighted for the respective centroid. And then, as you can imagine, SVD of Z. There is nothing hidden, eh? SVD of Z, and then you retain a certain number of dimensions. What is the maximum number of dimensions? And this sum of squares here, okay. So this total inertia is the chi² divided by n. Also here the proof is very easy to show it. Once you know that this matrix Z has this form, you take the sum of the squares of this, and then you nothing but the chi² divided by n. But note that the approaches were completely different, because with the chi², there were the theoretical frequencies, and then you wanted to see the deviation of real with respect to the theoretical frequencies. Here you start with row profiles, with column profiles, the distance from the centroid, the weighted distance, but the total variability is exactly the same. The sum of squares of the elements of matrix Z. Isn't it incredible? The goodness of statistics, that with completely different approaches, exactly the same thing. And therefore the Kramer index, therefore is, which is an index which is in between 0 and 1, because you take this coefficient and then you divide it by the maximum value. Therefore, the maximum value that the total inertia can assume is the minimum between number of rows -1 and the number of columns -1. Therefore, if you have a table, for example, which is 13 plus 4, which is the maximum value of the inertia, is 3. So the minimum between I minus j and I minus 1 and j minus 1. No. Here there is, why there is this comma remained here? No. Okay. Doesn't enable me to remove this small comma here. Anyway, do without it. So, there is a table which summarizes everything. So we have capital I row profiles in the space of dimension capital J minus 1. The similar thing is for the cloud of column points. Then the masses are the importance of each row, and here you have the importance of each column. The centroid of the row profiles is the vector of column masses. Okay. Here there is a chi-square matrix where the weights between two different rows or two are keep into account the inverse of the elements of C. Therefore, this is a chi-square metric. Similarly, the same thing for in the column space. Standardized profile matrix, which is, and this one is exactly the transpose of this. Total inertia, so therefore the sum of the squares weighted distances from each row profile to the respective centroid, or from each column profile to the respective centroid. The total inertia is the chi-square divided by n. The total inertia is the sum of the squares of the eigenvalues, the sum of the singular values. So that is the sum of the eigenvalues. Incredible, eh? At the end of the day, the singular values make it all. Sum of the squares of the singular values, this is chi-square divided by n, this is the total inertia. Therefore, in order to check the goodness of the analysis, well, you have this lambda, the squared eigenvalue, the square singular value divided by the total inertia multiplied by 100. Let us see. So you have this SVD, the number of dimensions to retain, and so you have this gamma, which is 2 times 2. Here the matrix is 3 times 4. So the maximum total inertia is 2, because 3 times 4 is the minimum between capital I minus 1 and capital J minus 1. So it is 2. Okay, so it is 2. Because I was equal to 3 and capital J was equal to 4. Therefore, you are in a space of dimension 2. UV, total inertia, and then gamma, the singular values squared, okay? The trace of this gamma squared is the total inertia, the sum of the eigenvalues. Total inertia is this one. The total inertia, therefore the sum of the squares of the elements of Z, which is also the sum of the squares of the singular values, that is the weighted variance, that is the sum of the squares of the distances of each point with respect to the centroid. Incredible. Incredible. So this is exactly the last row here. Don't you think it is incredible that you obtain exactly the same number? Incredible. Therefore, well, now you then, okay, analysis of inertia explained, and then you want to have a table like this. So you want to have the singular values, the eigenvalues, which are the squared, therefore the variance explained, or the cumulative variance explained. Here in the data lie in 2 dimensions. So the representation is 2 dimensions is exact. There is no loss of information. Nothing is lost. And now you plot the coordinates. These are the coordinates of the row points and the column points. You plot these numbers here. You compute then, and then you plot these coordinates of row points and column points. Okay. Now, the interpretation is very easy. People of Liguria tend to buy mainly the commercial brand. In fact, the people of Liguria were always known in Italy to be very stingy. Well, this is what in Italy there is a way of saying that people from Liguria now. I hope that there is no one from Liguria, but on the other hand, people of Lombardia or Piemonte, they are well known that they want to show off, that they have in fashion, that they buy the most expensive things because they think that you are much better treated if you have the most expensive products. And these are these 2 regions, Lombardia and Piemonte, that buy the industrial brand. People of Veneto, they don't care. They are hard workers at the end of the day. They're probably the first thing that they see on the shelf that they don't care. So this is really the analysis which comes out. So industrial brand and Piemonte, you see the angle between industrial brand and the first latent dimension here. So the first latent dimension explains 86%. Okay. Now you want to see, and this shows on the plot. These are the coordinates that are plotted. As in principal component analysis, where you have this matrix Z times V. Okay. The covariance matrix of Z times V is what? Is what? Now you can tell me. You make me happy if you tell me. So they are uncorrelated, so the variance-covariance matrix of the principal component scores, unstandardized, is matrix lambda, the matrix of the eigenvalues. Okay, once again, ZV times ZV divided by n minus 1, therefore Z prime divided by n minus 1 V, V prime R V, V prime V lambda V prime V is equal to lambda. Right. Now, here you have the coordinates, and the coordinates are dr to the minus 1 alpha u gamma. These are the coordinates. What is the covariance matrix here? Covariance matrix of this thing, but covariance matrix weighted. Right, because here you have a weight, the importance of each column. So gamma prime, u prime, dr to the minus 1 alpha, weighted. Okay. So, and then this is gamma, no. So this is dr to the minus 1 alpha u gamma. gamma prime, u prime, all this is the identity, u prime u, gamma. Gamma prime gamma, gamma is the diagonal, okay, gamma times gamma, lambda. Once again, right? So, therefore, let us see, for this is for all coordinates, is I times k. For the generic coordinate dr minus 1, for example, the first u1 gamma 1. Okay, this is y1. So you want to have the variance of y1, and so, okay, gamma 1 square u1 transpose dr to the minus 1 half weighted dr to the minus 1 half v1 gamma 1. Well, I already put yes. So gamma 1 squared v1 transposed v1, this is the identity, and so gamma 1 squared, the first squared singular value, and this is what is given here. So the variance of the H underlying component, the variance of the H component is given by the corresponding eigenvalue squared singular value. Therefore, the contribution of the ith row to the h-axis is given by this. Okay, this is a sum which goes from I to capital I here. Here there is a mistake, capital I. The sum which goes for all the rows. I don't know if there is in the book, but this is absolutely a mistake. Therefore, the contribution of the ith row to the h-axis is given by the single element of the sum with respect to the total. Right. And in fact, here it was written correctly. Right. So, therefore, the points with the highest contribution are called dominant points. And then you can do the same. That is, you can see what is the contribution of each dimension to the inertia of the point. The inertia of the point is the square distance. So this morning, because well, you know that I wanted to give all the details. Therefore, whiteboard 2. Anyway. Anyway, doesn't matter. So let me go to the practical implementation of this thing. So you have example of correspondence analysis. So you have a contingency table. N table. Okay? The only one thing that you have to do is Corana N table. That will do everything for you. Corana. Okay, automatically all the plot, then algebra, so you don't worry, but also gives you automatically in the command window, first of all, the summary, all the eigenvalues and the inertia which is explained by the different dimensions. You have the score and the contribution. You see, this means contribution of the point to the inertia of the first dimension. So the most important point is industrial brand, followed by commercial brand. On the other end, the point which gives the largest contribution to the inertia of the second dimension is industrial brand. Then let us contribution. These are the row points, then the results for dimension 2, and then column points. You have exactly the same thing. Then you have an overview of row points. You have the mass, the scores, then the inertia of the point. The inertia of the point is the distance of each point with respect to the centroid. Contribution of the point to the inertia of the first dimension, to the inertia of the second dimension, and contribution of the dimension to the inertia of the point. There are two things. Can you understand? The contribution of the points to the variability of the dimension. Contribution of the dimension to the variability of the point, to explain the variability of the point, to explain the distance of the point with respect to the centroid. So you see, these are what this means: relative contribution of points to explain total inertia of the latent dimension. The sum of the numbers in a column is equal to 1. On the other end, relative contribution of the latent dimension to explain the total inertia of the point. Now, there is another once you have obtained the output of correspondence analysis, there is the possibility of calling the so-called moon plot. What is the moon plot? Let me say something. The moon plot, given that what is important here is the angle between, for example, B and Piemonte, is the angle between commercial brand and Liguria, because if you draw two arrows from the origin, what is important is the angle. But at the same time, if there are too many labels, you want to put column labels around the moon. And so this is what you obtain with this representation. So you see that column points are represented around the moon. And therefore here, and the size of the label depends from the distance to the origins. Depends on the distance of the point from the origin. Right. Therefore, the larger is the label, the largest is the distance of the point to the origin. Therefore, Lombardia is close to the main centroid, even if it is shown at the outskirts of the moon. Okay, you see the angles here between Liguria and Marca Commerciale. So the angles here, that the angle between this vector and this vector is very small. The angle between this vector and this vector is very small. So it's an alternative, very nice representation. So let us see the science education. Science education, so the underlying file is science.xlsx. So this is the file, okay? the level of science and the level of education, and there are 871 respondents. Okay, you read this table, then the labels, you create the vector of the labels, or if you want to be lazy, you can apply Corana, and then with just one line of code, and then say you load the data, Corana, then it is a data matrix, and then you have the labels of the rows and the labels of the columns. Right, let us do it. Let us do it, and then let us interpret it. What is the dimension which is on the row? The first latent dimension explains 90% of the variability of the data, 90% of the total inertia. So therefore, the data lie mainly on a straight line. What is left out is the second dimension, which is 8.5%. So in this two-dimensional plot, you do not lose anything at all, because you explain the total variability. Now, so therefore, look at the first dimension, and it is amazing. Here there is, if you project the point on the first dimension, you have primary school, mid school, diploma, bachelor, master, and PhD. But that is incredible, because he didn't have this information that PhD was greater than master was greater than bachelor. You obtain the same results if you permute the rows. He doesn't have this information, but he finds this latent dimension, and this latent dimension is the schooling level. So as you move from left to right, the schooling level increases, and then there is this latent dimension. This is the latent dimension for the rows. But if you project this point, now primary, slightly favorable, not at all, indifferent, favorable, very favorable, you can see that as science, the level of science, the level of schooling increases, your attitude towards science increases. Isn't it great? Therefore, sometimes actually schooling, knowledge, science is much more than 100 words. That's science. That is what has to drive us for all our life. And now let us see that here primary school and not at all, therefore not at all, are mainly those which have just a primary school. And then very favorable is surrounded by bachelor, master, and PhD student, as you can see. On the other end, mid-school, indifferent and slightly favorable. And this is the power of correspondence analysis. So the theory underlying about row profiles, column profiles, then the algebra is very, very cumbersome. But the plot which comes out is really incredibly interpretable and very, very easy to understand. Or now, this was called Corana directly on the original matrix, on the original table. Or otherwise, you build the pivot table. So you obtain this table here. and then you apply correspondence analysis to the contingency table. Ah, no, with crosstab, no way. No, but with crosstab, then you have to put the row names, the column names to the cross, because crosstab gives in output, yeah, but it doesn't have the row names and the column names. So you have to manually apply, as I have done here with the pivot, because here X, here this matrix X, here you don't have the labels. Then let us look at the moon plot. You see, now they're very favorable, that is surrounded by PhD, bachelor and master. Not at all here, it is clearly visible that not at all is the direction of primary school. Right, and also indifferent is the direction of primary school. There are people who have a primary school degree that have answered that their position is indifferent. So you see the angle, which is important. On the other hand, slightly favorable is in the angle towards mid-school. So it's an alternative representation, which is really very, very nice. Then you can, if you apply this function Coran plot, then you can have a color, which is a color bar of column labels, which is the proportional to the contribution that each point gives to the inertia. So you can see what are the most relevant point, those which have the largest contribution to the inertia, and it is in this case master and primary school, which are those which are much distanced, you see, in this space, and they are on opposite side, these two. Well, and also PhD, look at the primary school, they are completely if you want, the angle between PhD and primary school is 180 degrees. This means that there is a very big difference between fully ignorant and fully educated. That is they're completely orthogonal. And well, so far, unfortunately, there is this column bar which goes on top of the labels. So we are studying how to fix it to put below the row labels. So first person that succeeds will be fully rewarded. But we have also investigated the people of matters to solve this problem. Now, well, in statistics, you want to have a confidence interval. In this case, you want to have a confidence interval of the position of the point in order to understand whether a row point is close in statistical terms to a column point or not. In statistical terms, a row point is close to a column point if the corresponding ellipse of the row points encircles the column points. This is the significance. So because you have a 90% uncertainty, where this is a sample, this is not the universe. So this is just a realization. But you want to have an inferential way, and you see that very favorable includes this bachelor, PhD, and master. On the other hand, not at all. Among those who said not at all, there is a very big variability. you see that the ellipse of not at all, that includes primary, mid school, and no, diploma is just outside. So the confidence level of the ellipses enables you to have an additional information. Finally, there is incredible that the cannot Corana app. Okay, so there is this Corana app. Why it doesn't give me the auto-completion? This is really mysterious. This is something that I cannot stand, that it doesn't give me the auto-completion. Corana app of our contingent, of our PVT. Okay, automatically gives you everything, and then this is a full app which enables you to control everything. And then the type of coordinates that enables you to switch between moonplot and the scatter diagram, the type of coordinates, and then it enables you, for example, to leave out a particular row, because you want to see how the results change if you leave out a particular row or a particular column. These are called supplementary points. And so the unit which is left out in this case is primary school, but the situation does not change at all. Then let us see another example with the ellipses. Example correspondence. Right. Let us see, for example, the car dataset. Car dataset out Corana car. Okay. Fuel economy, and then here it says that is associated with the Hyundai, Volkswagen, Kia, Mazda, and then style, Lamborghini, Jaguar, Land Rover, Maserati, Porsche, and Ferrari. You see. Now let us quality. These are, or let us, maybe in this case here it is much better maybe to have a moonplot. Okay, moonplot, and then you see that where there are Jaguar, Porsche, and Ferrari style, performance, innovation. Volvo is associated with safety. You see immediately the interpretation. And smart, value, fuel economy, you know, the small cars. So the interpretation here is absolutely easy and absolutely powerful. Now, let us see purchase type and profession. Let us see another example, or let me see if I wanted to tell you additional thing. That was the comment on the plot about the example of science and education. This doesn't add anything with respect to what we have just seen. Customizing. Okay, maybe we can do the. Let us do this house tasks dataset. House task dataset. This is a dataset that is I cannot stand that the auto-completion does not work, therefore I will have to relaunch MATLAB. Okay, load. Okay, now the auto-completion finally works. Load house tasks and house tasks. When you load a dataset of FSTA, house tasks dot properties dot description, you can see the description of the dataset, right? So, Corana, house tasks, because this is already the contingency table. Okay, how do you interpret holidays? Holidays, they are decided, okay, jointly, it makes sense inside the couple, they are decided absolutely jointly. And therefore, well, this is, okay, now if you do it in Italy, well, maybe this as an memento, maybe you see the husband that does the repairs and driving. At least in my family, this is still true. Okay, you see that, for example, alternating is the official documents. Sometimes the husband, sometimes the wife, and then you see the what is associated there with you see with the wives, and then you see that tidying dishes and shopping, they are intermediate between wife and jointly. Can you see this point? This is absolutely in between. Let us see in terms of Corana app. And let us see the moon plot. Okay, the moon plot with the husband, wife, and joint. You see the direction. That is very clear, eh? The direction of the angles. Now, let us see now the last example, which is called the clothes data. So let me describe. There is, I don't know if you know the Joint Research Center of the European Commission. Is when you hear about the European Commission, for example, is negotiating the fees, then there is a joint research which studies all the imports, all the exports, and tries to fight illegal behavior. And then, we have been working with these people for the last 20 years. And so we also had big results in terms of money that has been illegal frauds that have been found. And so this is an example in which you have all the 28. There was also Great Britain up to some years ago. Now there was the Brexit. There was also Great Britain, and then these are the level of price in which goods are imported into the European Commission. So 134 for Great Britain. This means that the level of price X1, the smallest level of price, has been observed for Great Britain 134 times. So here you want to understand which are the countries which are tricking the cars, which are the fraudsters. If there are countries which try to import goods from outside Europe at a lower price, not to pay duties. Okay? Because if everything is fair, there should be independence between the countries and the level of price. Maybe with poorer countries, maybe you expect that the goods come at a lower price. But here, for example, there is, let us see all the tables. And then there is also Netherlands. And, or for example, Netherlands. Here, for example, if a ship comes from China to England or to the Netherlands, the cost is the same. Therefore, if it goes to Dover in England or to Rotterdam in Holland, is the same. The cost is the same. So the price should be the same. But if the ships from China go mainly to Rotterdam, means then the price that the duties they have to pay, maybe the controls are much smaller. So you see the underlying problem. The underlying problem is that you want to see whether there is a relationship between the rows and the columns. Okay. Corana, clots. Okay, so that is the plot. The first time that we saw these plots, we were really very, very surprised. Because actually, it does not know, the computer and the correspondence analysis does not know that x1 is smaller than x2, is smaller than x3, is smaller than x4, and is smaller than x5. But it still finds this underlying dimension, which is the level of price, that is, as you move from left to right, you pass from x1 to x5. Right? Then, and what are the countries which mainly work with this small level of price? Malta, Great Britain, and Slovakia. You see these three countries. And, okay, due to this and, let us say, other analysis that have been published also with the robust correspondence analysis. Then there was a sentence of the judge, and the sentence of the judge which condemned UK to pay 3 billions, not 3 millions, 3 billions of euros. And there was the judge which said that the statistical analysis was robust and was appropriate and was stable, which is what we are doing. I mean, the robust correspondence analysis which does not depend on the presence of atypical observations. In this case, atypical observations are potential cases of fraud. So you don't want that the fraudsters who trick the card affect your analysis. And that's why robustness comes into play. Robustness in correspondence analysis, in principal components, in regression. I've dedicated all my life of research to robustness. Okay, so this will be my final frontal lesson with you. because next week there will be Professor Han. You will see me again tomorrow, and what can I say? I tried to do my best. You will let me know what you think. Thank you very much.